hello. Good morning to you. Welcome to 16.5, a lesson about buffers. So recall your strong acids. Hopefully you guys have them memorized by this point. Everything else is considered a weak acid. And your strong bases? Everything else is considered a weak base. So again, if you haven't yet memorized those, get on it. It's going to be pretty important. So let's consider the dissociation, or the dissolving, of the weak acid hydrofluoric acid, so HF. So HF dissolves into hydrogen ions and fluoride ions. But because it's not one of our strong acids, it doesn't dissociate every single time. Remembering Le Chatelier's principle from a couple of chapters ago, consider what would happen if we added some H plus ions to the system. Adding H plus ions would shift towards the products, or towards the reactants, and we'd use those H pluses to form HF, hydrogen fluoride. So we'd move in the reverse direction if we added H pluses. And that brings us to buffers. In fact, that would be an example of a buffer. So consider how important buffers are. Adding just 0.01 mole, 1/100th of a mole, which is only 0.36 grams of hydrochloric acid, to pure water, and you're going to change the pH from 7 down to 2. In biology, a pH range is incredibly important for your enzymes to function, for life to continue, and so our body has to regulate and stay within a practical pH. What if you ate 0.36? Again, think about that. A paperclip is 1 gram. So you're talking about a third of a paperclip. That's not much. So it doesn't take much hydrochloric acid to change the pH from 7 down to 2. And our bodies have to keep a pH between 7 and 7.7. So we have buffers, which are oftentimes weak acids or weak bases, and they're conjugate acids or conjugate bases. And these are what act as buffers. So here's our formula from before. Hydrogen fluorine breaks down into H plus and F negative. So we've already looked at what would happen if we added acid to this solution. Again, adding acid would be adding H pluses, and that F negative, that conjugate base, would snatch those up and move in the reverse direction. What if we added hydroxide ions, a base? In this case, if we added a base, we'd be, in essence, removing hydrogen ions. Those hydrogen ions would react with the hydroxide ions to form water. So this would be removing H plus ions, and that would push the reaction in the forward direction. And ultimately, we'll end up replacing the hydrogen ions that we lost. Perhaps you can see how this would be a good buffer. Buffers maintain the pH. That doesn't necessarily mean they always work at 7. They don't necessarily work at 7. That doesn't mean they always have a low pH that they maintain or a high pH that they maintain. Hydrofluoric acid would definitely have a low pH, pH of 4, give or take. But it would maintain that pH of 4. Adding base would snatch up those hydrogen ions, and our hydrofluorine would just break apart and create more hydrogen ions and fluoride ions. Adding acid, and our fluoride ions, would snatch up that H plus and return to HF. So that is a buffer. We're maintaining our pH. We're not getting any more acidic. We're not getting any more basic. We're just staying right where we are because of these reversible reactions. So eventually, though, you're going to run out of your weak acid or weak base. You're going to run out of your buffer, and that's what's known as the buffer capacity. If you continue to add acid, continue to add acid, continue to add acid, eventually you won't have enough of those fluoride ions to snatch up the H plus and move in the reverse direction. So the limit, the maximum amount that a buffer can resist change is what's known as the buffer capacity. And then it should go without saying, but the more of the weak acid and its conjugate base that you have, the greater the buffer capacity. So buffers are best when you have an equal amount of the acid and its conjugate base, or its dissolved form. So when you're at equilibrium for the buffer. So for that reason, buffers have different ranges that they work best at for their pH. All right, taking a look at a titration curve. The red line shows a strong acid and a strong base. So we have an equivalence point at 7, our H plus and OH negative equal at 7. Again, the reason why we have this general shape is consider how pH works. At first, you're adding small amounts of base, and you have very little change to the pH. As you get closer and closer to 7, pH of 7, it takes little base to change that pH. So a change of 1 pH around 7 is only 1/10 of the change around 6, which is only 1/100th of the change around 5, and it's only 1/1000th of a change around 4, and so on and so forth. So it takes less and less base to change the pH as you're titrating. The blue line is a weak acid.
Someone was playing Super Mario down here for a second.
The jazz?
I just hear that.
So a weak acid, the blue, has what's called a buffered region. So we notice this initial jump in pH, and that occurs until our conjugate base and weak acid have equal concentrations. Again, we have that until we reach our buffered region. Once we reach that buffered region, now we resist the pH change. So keep in mind here that our initial concentration of HF wasn't at the ideal buffer region. It was a little stronger acid. But as we added base, we reached our buffered region, and that's where our buffer works best.
Same coffee maker I have at home.
You miss your coffee?
I go through coffee makers about every year.
I was just about to say the same thing.
They just wear out.
Yeah. Yeah. Very, very useful tool, though.
Yeah. Oh yeah.
So we notice eventually we reach the end of her buffered region, around 25 milliliters of titrant, and we have exceeded the buffer capacity. That's where we see the upshoot of pH. All right, so acid-base indicators. These are used to indicate and detect the equivalence point. Again, they work in Le Chatelier's principle as well. The idea being that the anion has a different color. Well, not necessarily the anion. It could be a base as well. But when it loses that hydrogen ion, or it loses the hydroxide ion, it has a change in color. Different indicators have different regions at which they will dissolve. So it's very important that you change your or select your indicator correctly. All right, a couple of other points here as we finish up this unit. Polyprotic acids. So remember, some acids have multiple ions that they donate. So acylic acid, H2C2O4. See the two H's out in front there? It can lose one H. Then you're left with HC2O4 negative, which can also lose an acid. So each of these are their own acid. So because it's a weak acid, both of them are weak acids. H2C2O4 is a weak acid. That makes it also a buffer. HC2O4 negative is also a buffer. And so each of them has their own buffering regions. One for each ionization. So we see the general shape of the curve here. Here's where we would lose that first hydrogen ion, and we go from H2C2O4 to H plus and HC2O4. Then we reach the buffering range for HC2O4 negative when it goes to C2O4 and 2 negative, in this buffering range here. So a quick question, if you wanted to use HC2O4 negative as a buffer, what would its buffer range be? Well, it's certainly above 6. Call this 7, so somewhere around 8. pH of 8, it looks like, is where this would be the best buffer. It would hold your pH around 8. There are also triprotic acids. So tri meaning 3, and you're going to have 3 equivalence points here, just something to point out. Here's your first hydrogen ion coming off. Here's your second, and there's your third. You can notice the shape of the graph for a triprotic acid. All right, so homework 16.6, a longer homework. You have 2 days to get it done. It's also your test review. So take a look. Hopefully you guys are doing well with acids and bases and are ready for that test on Friday, April 19th.